Hello, I'm Mark Hollister, and thank you for that introduction. So my research work that I have been currently working toward is augmenting spatial awareness for exoskeleton users with augmented reality. So the first question, perhaps, well, I guess I might as well talk a little more about me for anyone curious. I'm from Dallas, Texas. Generally just love computers, product and UX design, gaming and outdoors work. I have my bachelor's degree in industrial design from Auburn University, which is kind of what started my journey toward all of this. I've always wanted to design new products, new inventions, more from like a user-centered design perspective. Starting from Auburn, that kind of led me to do some internship work at NASA, as my senior project was designing a Mars rover along with some of the people at Marshall Space Flight Center. Along with that, led me into doing internship work at Langley Research Center with microgravity medical workstation design. And that's what got me into XR, mainly virtual reality at the time, as we used it for prototyping and evaluation. And there I also discovered human factors engineering was a thing, as that's what they had a lot of people doing there. And that's what got me onto my journey of pursuing a master's degree here at Virginia Tech, because I wanted to learn more human factors engineering, learn more about virtual reality and augmented reality. And along with that, I also continue doing intern work such as lunar surface habitat design and software UX design for NASA, Marshall, during school breaks. But that's what led me to where I am currently right now, researching augmented reality along with the rest of the Weave research team for whole body exoskeletons for advanced vocational enhancements. The Weave team is sponsored by National Science Foundation and Human Technology Frontier, and also working with Sarcos who provides the exoskeletons that our group has been using for our research work. This whole endeavor has been led by Dr. Srinivasan in the Human Factors department with Industrial and Systems Engineering, and along with several other co-principal investigators, including my advisor, Dr. Nathan Lau, who has been advising me for getting this whole research efforts going. Or at least I'm one of the members for this whole effort. There are several others who have contributed to this, and I'm just one of them within the Virginia Cognitive and Systems Engineering Laboratory. But we actually just changed the name of our lab, I believe. So we might no longer be called VAXI. Think SCEL or Systems and Cognitive Engineering Laboratory or something like that. But anyway, so this has been greater efforts regarding making exoskeletons easier to use, easier to control, and I've been helping toward the augmented reality side of things. Sorry, go ahead.
Mark, if it matters to you, what's going out on Zoom is your presenter view.
Oh.
And I've had this happen to me when I've tried to do this too. I think the only solution is mirror your screen instead of extend.
Yes.
Because I don't know if you can. So if it doesn't matter, continue. I just wanted to give you a heads up.
Oh yes, that's fine. Thank you for letting me know. I'll just here we are. Let's swap the display or duplicate. There we are. And I believe it's
there. You
now.
go.
Great. Thanks. Oh yes. Sorry, I just didn't get the.
Hi, Graham.
Yes, go ahead.
Yeah, so I'm Graham. Well, actually, I didn't really prepare any statement. So basically, I've been working on this project as well. So I sort of with Chaitanya, as you see there, originally got the spatial awareness program, AR platform up and running. And Mark obviously took it over and perfected it. And as you can see later in his presentation, what I'm working on this project right now is that since there's obviously some balance issue, force output issue that the users might experience, currently we're trying to attach some IMUs on the user and basically figure out how to display their force output to them so that they can know that what they're putting is what they're not actually experiencing. So that's the problem that I'm working on right now. Unfortunately, it's still a very in the infancy stage, so I don't have anything to show here right now, but Mark will keep you guys entertained.
Now, are you an ISC also?
Yeah, I'm an ISC also.
Okay.
Yeah.
Are you a master's or PhD? or-
PhD with Dr. Law as my
Okay.
advisor as well.
You guys say hi to Nathan for me. I haven't seen him in a long time.
Yeah, actually, he was wondering about like, if you were doing all of this stuff, still just like about a week ago when I asked him, so yeah, I'll say hi.
Yeah.
Yeah, sorry for forgetting to introduce you. I get really robotic on like how I follow my slides directly, and yeah, without a slide for you as well. Yeah, I completely forgot. But anyway, so yeah, that's what we have so far, and yeah, you'll see some more pictures of Graham's work as we get going through here as well. But for now, a little more context. This is the problem with exoskeletons, basically.
Turn.
Have it again.
All right, so those two examples, even though a bit comical from movies, are actually very real problems with modern day exoskeletons as they are currently are in their current form. The thing is, because full body powered exoskeletons, such as the type that we would like to envision for future application, because they have mismatched human proprioception and kinesthetic cues and feedback for the user, this makes them very unwieldy to control. People almost have to kind of like relearn how to move and walk when using an exoskeleton. This creates cognitive demands, and they focus their attention on just how to control the exoskeleton rather than perhaps their other tasks, or even if they can focus on both their task and controlling the exoskeleton, it might be at the cost of situation awareness and spatial awareness. And because of this, it increases the likelihood of collisions with whether it's nearby objects or other people. And because exoskeletons amplify the forces of the user that they exert, you can damage equipment, you can injure other people, or even themselves, potentially. And this kind of contradicts almost completely counterproductively the point of using exoskeletons in the first place. We want to have exoskeletons, at least for industrial users, in order to alleviate things like repetitive stress injuries. And if you're just causing more injury when you're using the exoskeleton because of this lack of situation and spatial awareness, then we're not really accomplishing much by providing exoskeletons. Sure, we may have amplified strength, but if we're still getting injuries, just no longer RSI, but now just collision injuries, that's not really much of an improvement, is there? So how do we solve this? Well, short of improving control methods for exoskeletons, one way is to augment the spatial awareness of the exoskeleton operator. So we have been considering so far augmented reality, as that is one of our main approaches to this. There are a variety of approaches that you could use, auditory alarms, tactile vibrating proximity displays that you can place on the user or something like that. Currently, the focus of our work has been entirely on visuals, however. It is possible that augmented reality could mitigate these spatial awareness reduction from using exoskeletons, and that's what we're trying to find out. One of the, or at least a few of the potential options that you could use are rear view mirror or radar displays. At least that's often some of the common solution ideas for how you would give someone more spatial awareness. So that's one thing that we are investigating. Another aspect to our work that we are considering investigating is potentially improving the usability of exoskeletons through things like momentum displays. We'll get to that in a minute. That could also be done through augmented reality as well. So looking into some of the prior work that has been done before I got started on this, there's been a lot of work done on at least that I've found so far. But of everything that I found, it seems to generally focus more on partial body exoskeletons, sometimes even just passive exoskeletons, and not necessarily the exact same application that we are looking for. Although they do have similar problems. They do look into various solutions, including improving awareness or improving control methods, but it doesn't seem completely applicable to what we are focusing on so far. And the same thing goes for visualizations for collision avoidance. Even though some of these studies do exist, they don't seem to be in the context of industrial exoskeleton use or optical see-through AR headsets, or even the exact type of visualizations that we might expect to be employed in an industrial setting, like shrinking the size small enough so that way it does not impede your field of view, allowing you to do your task. So we felt that there was a little bit of a research gap that we could address, and the whole Weave effort started tackling this through a virtual reality study, and we investigated, at least Graham has had more experience in this than I do, so feel free to chime in if you have any comments. Investigating in things like different perspectives of viewpoints like rear view camera or bird's eye view or 3D arrow to determine whether or not a sort of collision avoidance display, which might be the most effective. And doing that with some simulated primary tasks like this whack-a-mole game to try to determine which one was most effective at helping prevent collisions. Eventually, we decided to transition to full optical see-through AR headsets, such as the HoloLens right here. If you don't have any comments, I could.
I'm fine.
Okay, that's fine.
Yeah.
Just making sure. So before getting into that, this is about the time when I came onto the project. One thing I noticed is we're just still kind of focusing on just your typical radar and rear view mirror. I'm thinking surely there have got to be other more different solutions that could possibly work. So I did an informal survey of various, shall I call them spatial displays, because radar, kind of implies the technological solution of like ranging and distance estimation via a light wave. So I'll just call them spatial displays. Oftentimes we think of the typical overhead radar as seen, whether it's in aviation, whether it's in video games, everyone knows what it looks like. This is from Halo. A lot of people may be familiar with a design like this, but the cool thing about at least the video game industry is that it's absolutely rich with various different implementations of every single type of radar you can find. You have things like elevation display via leader lines over a horizon plane. You have information encoded on the radar, which granted has been done in aviation as well. You have things like rotational encoding in the radar display, such as in flight and space simulator games, we can have a horizon displayed on the radar itself. Then, if you want to expand your idea of what a radar is, because a radar is just something that tells us something is there and where it is in relation to us. It doesn't have to be like a circle with concentric rings and blips on the radar. The damage indicator that you find in many video games, often being a ring around the center reticle or around the sides of the screen, can also count as a radar, or even just arrows pointing somewhere. That tells the presence of something and its position relative to you. So technically that can count as a spatial display and thus something to be considered when investigating. are potential solutions. If you want to get further into everything, you have projection-based systems where it's like almost like a secondary viewport or scope where you it might not necessarily show the distance as well, but it definitely shows the azimuth and rotational elevation or relative to you. And it could encode proximity, like by the size of the dot or something like that. Often seen in flight simulator or space simulator games. This often can be done if you are looking for things that have elevation or altitude or rotational elevation differences as opposed compared to your current location. And thus you can get orientation information encoded right into the radar itself as well. If you really want to stretch the definition of what a spatial display / radar is, you could do even more crazy things like encoding the color of the heads-up display to show radar or hit detection location, such as we see in the upper right there. You got hit on the lower left-hand corner of the screen, or compass marker systems or screen overlay markers, such as you see in Call of Duty. You can overlay map information, as on the left example from Crisis. You can do 3D maps if you really want. That's what that's an interesting thing to do. And you can even consider highlighting from whether it's augmented reality, whether it's thermal vision, overlaid over night vision. That could also be considered if it's like a rear view or side view camera based highlighting visual, such as on the lower right there from, I believe, Ghost Recon. That could also be considered a form of spatial display. So looking into this survey of different types of radars / spatial displays, I kind of grouped them into 4 categories, at least for my purposes. I don't know if there's an official definition on these, but this is just what I grouped them into, based kind of on the whole method that they decided to employ and the goal that they were going for, that being overhead, direction ring, projection based, or hybrid. The funny thing is, looking into real life examples of radars, I kind of found similar directions for the way these things are designed. You have your classic aviation type radars that kind of have an overhead view point, or you have like in military applications, night vision and thermal vision, or thermal fusion as they sometimes refer to them, cameras, which given rear and side view viewpoints could be considered a spatial display. And even in augmented reality research and development, we see things like the direction ring, which is the ARC4 solution developed for the military, and for augmented reality optical see-through headsets, which I believe stands for Augmented Reality Command, Control, Communications, and Coordination, I believe. But yes, augmented reality displays for military make use of that direction ring type of system. Or also like the research I previously mentioned, making use of a projection radar type of system. So looking into these, I started trying to come up with research questions that we wanted to address. Kind of starting to look more into like, what are the cognitive aspects of all this? How do we determine the ideal UI design characteristics to make for the ideal spatial awareness display? Things that I found was that there are some differences between use of foveal and peripheral vision. Like the overhead radar seems to make use of more foveal vision, whereas the ring radar seems to, at least depending on how you implement it, may make more use of peripheral vision. Depending on the way you implement it, once again, you can add different display angles for the radars, giving them like a 30-degree tilt or versus just plain 90-degree flat display. That could potentially cause interaction effects for the how well each type of UI design performs. And so our goal is to figure out is there an ideal implementation of these radar displays? Which type is it? Is there a foveal peripheral vision based difference? What is the ideal angle? Which there has been some research been done, but again, not necessarily in the context of what we are working on. And is salience or abstraction a potentially determinant feature? Like you could easily say that someone may find that a radar performs better than a rear view camera. Well, that may only be just because you color the dots bright red or bright green, and they can just notice it more easily. So there's potentially a third interaction effect that could be had there, unless you at least control for it in the experiment. So going into this research, which the experiment has not yet happened. That's currently something that I'm still working toward, but this is the current plan that I have so far, at least. Testing different types of radar display, different perspective angles for presenting the radar, and also comparing that to a rear view camera and adjusting for salience there. Now, this is still subject to change because this particular type of comparison of experiment conditions may be kind of tough. Since not all of these directly compare to each other, one could say the rear view camera isn't really comparable to the other two. But for practical uses, it's easy to foresee someone implementing a system like this wanting to prefer a rear view camera over a radar. So we think we find it potentially wise to compare them anyway, because realistically, someone's going to want to choose between these systems, even if they are not directly comparable. So this is what we are considering investigating: the different salience levels, at least for the or abstraction levels for the rear view camera, as well as radar type and perspective angle for the other radars. These are all, by the way, concept images that I've created from in Photoshop. And this is kind of the goal that we are trying to achieve with our current setup right now. This is ideally how we would like for it to look, assuming all displays were turned on at the same time. Of course, things are still subject to change, but that's currently what we're going for. So our first attempt at this, we used a Magic Leap system, which we currently switched to the HoloLens now, as that's easier for glasses users, and also a variety of other development improvements that we found. And we also use the HP backpack computer to run this whole system. Not that ideally we want to depend on the backpack computer from like a practical perspective, because like they're already wearing an exoskeleton. We don't want to have them to have to wear a backpack. It's just for development purposes, makes it simpler and easier, especially since webcams are not actually supported by the HoloLens in the whole USB driver. You can't actually connect a webcam even through a USB hub if you tried, at least as far as I know, or at least without rewriting a lot of the driver yourself. So yes, we have the two webcams connected to the backpack computer right there via a camera rig. And we've already done some preliminary testing based on the Magic Leap system. Graham and Chaitanya have previously been working on a lot of this, and they have a system going using computer vision with Monoloco. Monoloco uses computer vision to detect the location and distance estimation of any people that it sees in the webcam. So we just feed that info directly into Unity, and that's how it all works there. And for the initial prototype, we also started looking into momentum displays. That red bar that you see there is our attempt to start thinking about how we might implement momentum displays for figuring out how to get people to learn how to control the exoskeleton more easily. Like, for example, in this image concept, pushing the cart, you might be able to see something like a stopping distance display, so you can know with the amount of force you're pushing with the exoskeleton, how much distance will it take for you to stop, or simply a velocity meter as well. ideally, we would have like one of these for each limb, like maybe a ghost limb being projected in front of you so you can figure out, okay, where's my arm going to be in the future if I keep going this fast or something like that. The momentum displays haven't is something that we are still working on. It's something that we are not ready to show today because we don't have a working implementation, but this is also something to that we are working toward for the whole exoskeleton weave project, trying to see if AR can help people control exoskeleton more easily, as that would also indirectly improve spatial awareness if they don't have to devote so many cognitive resources to controlling the exoskeleton. Reasons for that, of course, can be for things like, of course, preventing people from accidentally crushing objects with the exoskeleton, or denting metal shelves by pushing too hard into them. Things like heat maps for force application and other various things. And ideally, we are looking into using motion capture in order to simulate a full body momentum display in the future. But yes, because we're not there yet, currently what we have is our augmented reality spatial display system. So now let me see if I can. I'm going to keep sharing. Let me switch to Parsec here. Okay, so our system is built with Unity, and we are using Monoloco for our computer vision system. There we go. So I'm running Monoloco now. This is essentially just our computer vision system, or at least that we've adopted and is using to estimate the location and like the exact location of anyone that it sees right there in the image. As you can see, we have two people in view of the camera right now. It detects not only your position, but also an estimation for the skeleton of the user to try to get almost like a sort of completely computer vision based motion tracking, motion capture into the whole system. Forgive the slow update rate. That's something that I'm still looking into solving. It should be much more real time than it looks right now. I'm actually considering switching to Intel RealSense in order to speed this up, if I can figure out how to make this work. I think it's a problem with it not using CUDA acceleration effectively. But yes, Monoloco is what we're using right now for determining position of people, and potentially we might switch to Intel RealSense or Azure Connect as well. So that's it for Monoloco. All that information, as seen right here, is being piped out directly into Unity, which is HoloLens, I think is off, which is connected to the HoloLens. We are streaming the internet, the video over Wi-Fi to the HoloLens, since that was just the simplest method that we had available. Ideally, once again, this whole system wouldn't run directly on the HoloLens to prevent the need for an additional backpack computer, but for now, we're just using the PC, as that makes things much more simpler for development. Okay, so now I'm streaming video to the HoloLens, and let's play the Unity. And now, there we go. There are my displays. And now, let me show you what I'm seeing in the HoloLens. There we are. There we are. Okay, so I'll get up and walk around a little bit. Actually, yeah, I don't even have to wear the backpack. Well, actually, let me see if I can put it on so that way it'll show the rear view mirror a little more easily. I'm gonna leave that monitor plugged in since I forgot to take it out earlier, and it might make things weird. It's very sensitive to monitor connection. It's like if you disconnect the monitor, the whole thing will freeze. Even though I have a dummy plug for the DisplayPort video in here, it's kind of finicky with transferring the system. But you can see here, I'm on the backpack computer, and with the webcams attached, you can see the camera just moving around as I rotate my body. And
Maybe a little bit.
Yeah,
Detected people. They're sitting down, I guess.
yeah, the problem is monoloco sometimes freezes up a little when it's no longer detecting people. There we are. So yeah, sometimes if monoloco no longer detects people, it sometimes freezes up and things just kind of disappear. But yes, you can see all three systems kind of working right now. The radar, the overhead radar, as is on the lower left-hand corner there, the ring radar in the center, and of course the rear view camera in the upper center. And this is all still, of course, a work in progress. So everything from the slow update rate to the field of view of the camera, which also we now have a 180-degree camera that we also have for a potential rear view camera use there. So that's cool. That's coming up. But yeah, that is our system. All of the information from monoloco fed to Unity is now being displayed on our radar systems. And that is the current state of what we have going. If anyone has questions right now, I would be happy to answer them.
I don't have a question, I have a comment. I don't think I would worry too much about the backpack aspect because I don't build exoskeletons, so I don't know what I'm talking about, but like they have computing, I would assume built in, right?
True.
So, and like toasters run on GPUs now, so like all you need is a GPU. Seems like that could be incorporated into the design of an exoskeleton, you know what I mean? So
Yeah.
I don't think I would feel like you have to apologize for the backpack, like unless someone gives you an exoskeleton to play with, you've gotta.
Yeah.
All right.
Yeah, true. I suppose as long as it doesn't cause an inconvenience for the exoskeleton wearing itself,
Yeah.
might be all that really matters. I
Yeah.
suppose.
In a design sense, you could just implore people to add the needed GPU that you would want to use to whatever computing is already happening on the exoskeleton. There you are.
Yeah.
To kind of piggyback off of that, I'm assuming all of the computing is done like on the platform itself, like so essentially like the computing for like computer vision is done on edge, right? Or on the device.
It's done on the backpack computer itself. It's running all of the computer vision and the Unity build that is running all of this.
So would it be possible to like somehow use like cloud compute then?
If the latency is low enough, yes, cloud compute could be used, I figure. Latency seems to be the
Yeah.
real issue there, as with many types of cloud employments of XR systems. But yes, if possible, that's certainly a potential solution.
Yeah, because my first thought was just like you could, I guess, port like the computer vision portions like to the cloud, and then provided that latency is good enough, then you know that could be piped into like the Unity application, and that would be a way to speed things up.
Yeah.
So yeah.
Yeah, certainly could be, or even if it's just a local sort of cloud thing.
Yeah.
Like actually, yeah, you just said edge.
Yeah.
So yeah, anything like that certainly could help things a lot more. Yeah, that's great.
Have you explored at all? So I noticed that the HUD display is relative to your body rotation, not your head. I'm assuming because you're not necessarily tracking the difference. Have you explored whether that might have any impact on understanding of the data?
Yes, actually, there are several considerations. One is that the camera is mounted to the backpack, so that's like torso referenced, whereas my heads-up display is mounted to my head. So if I turn my head, the what is it? The readouts that I have on my system does not necessarily turn with me, with my head, and people could confuse that unless they're like somehow familiarized with the idea of it relating to their torso. So I'm actually considering for my future implementations to like 3D print a HoloLens camera mount, so that way I can put the webcams directly attached to the back of the HoloLens, or make it so that the radar is somehow relative to your body. Like maybe you see it in perspective in front of you, and as you turn your head, it kind of like rotates with you as it goes. I'm not sure how that would work yet. Right now, I'm kind of more focused on the idea of mounting the cameras to the back of the HoloLens, and that would solve that aspect at least. There are also a few, like time permitting, there are a few interesting ideas. Like some people would say that this is technically not augmented reality, it's heads-up display. Since it's not like registered to the physical world in 3D space, at least that's the definition that some would use. And for that, I'm wondering like, well, what if we were to try to start registering some of this to 3D space as well? That's another thing that I am thinking about. Haven't quite done much work there because I don't feel like it's not in the scope of what we are currently focused on for the moment. But yes, I've been looking into the whole screen versus body reference subjects there.
I have a question about
Yeah.
what is like the field of vision for the back, the camera at the back, because I can see from the radar that like the front view is kind of really small because of, I would assume it's because of the field of view of the AR display. But like
Yes.
the back is kind of large. I just wonder what's the.
Yes, the field of view is kind of a limitation right now, really. What we have here, the AR display, is basically at the limits of my field of view already for the HoloLens display. I've already pushed it as all the way out to as far as what the HoloLens field of view will let me. Beyond that, it's a matter of what becomes better for usability and legibility at that point. But yeah, just because of system limitations, this is where I have in place right now. It definitely is a HoloLens field of view limitation there. There's also a camera field of view limitation, at least on this one. The current camera that I'm using has about 90-degree field of view. And as I mentioned earlier, we now have a 180-degree camera that I'm starting to do my future development work on. And we'll at least be using that for the rear view camera. Whether or not it gets used for monoloco because of image distortion issues, we might switch to RealSense anyway, so we'll see how that goes there. But at least for the rear view camera, we are going to be switching to the 180-degree camera there too.
Got it. Thank you.
Have you thought about exploring disconnecting the information? So maybe the heads up, maybe the camera is connected to the backpack. It's always showing what's behind your body, but the radar might be showing spatial information around you relative to your head.
That could work. That could work. That's not something that we've looked into because, again, the scope of this study has mainly been focused on like comparing which visualizations are best just for the purpose of collision avoidance. Which actually, with that, I might want to. There is like 2 more slides that I have left before we run out of time. Yes, we are open to at least future looking into whether it's other modalities such as auditory and vibration, tactile displays, or whether it's separating the what's the term? I forgot what you how you refer to it, like separating which radar has different like reference frames. Yeah, we can try that as well. Yeah, right now it's just a matter of research. So So we haven't looked into that yet, but thank you for letting me know. That's something that I will take note of. All right, just 2 more slides. We're just about. After that, yeah, I'm definitely still available for any other questions you may have. Yeah, presenter view again. I need to change the
Online,
default
so
setting.
no one, yeah.
There we go. I need to change the default settings on this thing. I guess I don't present enough to have thoughts.
I think it's Zoom, I don't know.
Yeah. Okay, so currently, we are considering evaluation study within subject experiments testing these 3 display types with their different display angles, which we actually didn't show. Well, actually, the ring radar that you saw was already at a 30-degree tilt, whereas the overhead radar was at 90 degrees. But yes, exploring these at different display angles. And also potentially using the mirror either as a control condition or maybe just having a control condition of no display. And instead testing the salience differences on the mirror, since that's also kind of an important question, research question as well. We're considering a task that kind of replicates a warehouse scenario, ideally, since we are hoping for a sort of more real world oriented experiment for more external validity. We're considering having 2 shelves or benches and having the participant move boxes between them, kind of simulating warehouse tasks and trying to avoid bystanders who may be next to them. Hopefully the IRB will approve that. Because like there's like the whole collision with a person type of thing. Although we do feel that it may be helpful to actually use real bystanders. So like a lab assistant serving as the bystander, moving towards specific locations for each trial. As a real bystander may sufficiently encourage collision avoidance. You know, like if you use virtual hazards, they might become complacent because they know that there's no physical consequence to colliding with the bystander. So at least our current plan is to use real bystanders, unless there's like a sort of more cognitive, psychological reason to have a preference for one or the other. We do have a few hypotheses for which radar displays might perform better. Personally, all said and done, I personally expect the ring radar to perform the best, as it is like it abstracts the information to the degree where it tells you exactly what you need and nothing else. Like you don't really need to know exactly how far they are away, as long as you know they're close enough that you need to avoid and where they are directionally azimuth in relation to you. Although you can encode distance onto the ring radar as well, which I have implemented with the thickness of the ring. But yeah, that's currently my hypothesis. Essentially, that's the ring radar will perform the best. And it remains to be seen if that hypothesis will hold. Some potential impacts for this would be that, for one, as exoskeletons start to become more widely available, hopefully improve spatial awareness, if this turns out to indeed be a potential solution for exoskeletons, could help realize the appetite on the desire to adopt and field the exoskeletons. So because then you won't have to worry so much about collision issues if we have at least some kind of system to help with collision avoidance. Hopefully this will increase spatial awareness, not maybe just for exoskeletons, but maybe just for overall various augmented reality applications, whether it's emergency response or military. Doesn't have to be exoskeleton. This can all generalize to various other fields as well. We may be focused on application to full body powered exoskeletons and reducing collision probability there, but this could potentially have wide generalizability. Hopefully that's all will come out.